explain parametric and non-parametric tests of the hypotheses that the population correlation coefficient equals 0, and determine whether the hypothesis is rejected at a given level of significance. We're going to look at two tests for correlation, a parametric and a non-parametric test. We'll start with the parametric test. What are our hypotheses? We've seen this structure before. Correlation is equal 0 versus not equal 0 for two-sided. If it's one-sided, we draw out our alternative hypotheses first. There's a left tail test. There's a right tail test. Correlation less than 0, correlation greater than 0. Then we know the null must be everything but what we've written in the alternative. And we have seen how to calculate a correlation coefficient before. It is just R, which is equal to the covariance of the two variables divided by each of their standard deviations. Each one of these things is a parameter, hence we have a parameter, hence parametric testing. This correlation, by the way, has a name. It's called a Pearson correlation. You may have seen it somewhere else or heard it referred to somewhere else as a bivariate correlation. Let's look at the test statistic that we're going to use. It is a T. It is distributed or T-distributed. The statistic is T-distributed, but it doesn't have the regular form that we would expect to see when we test means. Numerator is R multiplied by the square root of the degrees of freedom. We have n minus 2 degrees of freedom. And our denominator is 1 minus R squared. And just be careful with this denominator that you don't make a common mathematical mistake. If our R is negative, our denominator is actually 1 minus negative R squared. Not 1 minus negative R squared, but 1 minus negative R squared. Order of operations, right? Square the R first, then subtract it from 1, so that everything under the radical sign will be 1 or less. So if R equals 0, the amount under the radical sign will be 1. So the denominator will just simplify to 1, or it'll be something less than 1. But if you end up with something under the radical sign greater than 1, you've made a mistake. And the mistake you've made is probably adding R first and then squaring when you're subtracting a negative. Square it first, then subtract it. Once you square it, this turns positive. A big issue with testing correlation is, let's say I'm a researcher and I need to find significant correlations. Let's say that I need to prove a point and it's important that I find them. I can always just increase the size of my data set and almost any correlation becomes significant. In testing R, as n increases, H naught is rejected for even small correlations. In big data sets, almost any R will be significant. So let me show you. Let's say that we find an R of 0.02, which is saying that there's almost no relationship between those two variables. It's so close to 0 as to say that they're completely random to each other and independent. But we have 10,000 data points. So let's calculate our test statistic. This will end up being roughly about 2 because this will be very close to 1 and this is almost 10,000 times 0.02. It'll be roughly 2 versus a critical t-value of 1.96. So even something which is almost non-existent becomes somewhat, well, I shouldn't say somewhat, it's over the 1.96, slightly over the 1.96, so we'll call it somewhat significant. So that is an issue with calculating the parametric test for correlation. Let's do a walkthrough example 16. Examining the relationship between returns on investment 1 and investment 2. And before we jump into this, you might want to hit pause and in the reading scroll back up to Exhibit 1. There you'll see a scatter plot between investment 1 and investment 2 for 33 periods. And this is what this one is referring to. An analyst is examining the annual returns for investment 1 and investment 2 as displayed in Exhibit 1. Although the time series plot provides some useful information, the analyst is most interested in quantifying how the returns of these two series are related, so she calculates the correlation coefficient equal to 0.43051 between these series. Is there a significant positive correlation between these two return series if she uses a 1% level of significance? Let's think about our alternative hypotheses. What are we asking here? We're asking for a positive correlation. So we're testing the alternative that the correlation is greater than 0. So the null must be that it is less than or equal to 0. This is a right-tail test, 1%, which means what is our probability in our function call for the t-statistic in Excel? It will be 99%. Let's see what we have. State the hypotheses. Correlation is less than or equal to 0 versus greater than or equal to 0. Our test statistic is a t-statistic, r multiplied by the square root of the degrees of freedom divided by 1 minus r squared, the root of 1 minus r squared. Significance level is 1%. We have 33 minus 2 because this statistic is distributed with n minus 2 degrees of freedom. There were 33 periods, so there's 31 degrees of freedom. Critical value of 2.45282. Again, you're going to input as your arguments into the inverse t function because we want to get a critical t out. 0.99 because we only want 1% in the right tail, right? And degrees of freedom 31. We reject the null if the calculated t statistic is greater than 2.45282, and we'll enter our values in. There is the r, which is 43051, and 0.18534 is the r squared. This is the term in the bottom. Take the root of that. We get 2.65568. It is more to the right. It is more extreme in the right tail than the critical value, so we will reject the null. We reject the null since the calculated t statistic is greater than 2.45282. All right, let's look at a non-parametric test. And we would use the non-parametric test if the normality assumption for x or y is violated or we feel outliers are present, which will affect an R value or a correlation. We're going to calculate a Spearman rank correlation coefficient, which we denote as RS, which is still a correlation. We'll still use the same t statistic, except we're going to use this version of the correlation coefficient in there instead of just R. It's basically a correlation, but it is calculated on rank values and not the values of the observations of X or Y. So that's sort of abstract, so let's see how we do it. Let's take the X variable and we will rank all the X variables from the largest to the smallest. And then we assign ranks, 1 to the largest, and we count all the way down to whatever n we have, and n would be for the smallest. So if we have 100 observations, the smallest x would be 100. If there's a tie, we assign all the same rank to whichever values are tied. So it's an average rank. So let's say we have 3 values tied for the 6th rank. So position 6, position 7, position 8 are all the same x value. Add them up, divide by 3, we get an average of 7. They each get a rank of 7. Each get a rank of 7. Once we do that for x, then we do that for y. We do them independently and we rank them from the highest to the lowest. All right, after we have that done, we move on to our next step. We put the data back in the original form that we found it, x, y, x1, y1, x2, y2. So after we rank them, we put them back the way we found them. And what we'll do, we have the ranking on x1, we have the ranking on x2. We'll subtract the two rankings, we'll call that the difference, and we'll square it. Go to the next paired observation, the rank on x minus the rank on y, we'll get d, then we square it, and we do that for all the variables. So on the original data set, the pre-ranked data set, calculate d squared, which is the rank of xi minus the rank of yi squared, where x and y are the original paired observations. Then we'll calculate the correlation coefficient, R sub s, and it is 1 minus the term in square brackets. To understand why we're doing 1 minus, let's just do a thought experiment. Let's imagine that the highest value on x is also the highest value on y, all the way down to the lowest value on x equaling the lowest value on y. In other words, all the ranks are equal, so when we subtract all the ranks, we'd get 0. So all the d's are 0. This term would be 0. This whole term in brackets would be 0. 1 minus 0 is 1. And that's exactly what we would be saying. If they are all perfectly correlated, the correlation would be 1 because all the d's would be 0. That's why we have 1 minus this term. If the term in square brackets is less than 0, we will have a positive correlation. If this term is greater than 0, 1 minus something greater than 0 will be negative. This can't be larger than 2, just mathematically, so we would have a negative correlation. Then we can test RS. If n is greater than 30, we can use a t-test. If n is less than 30, we need different critical values. We're not going to worry about a sample size less than 30. For what we're doing, we're only going to look at sample size greater than 30 so that we can use the t-stat. It is the regular t-statistic for correlation that we've used, except here, in this one, we are using RS instead of just the Spearman correlation. We're using the rank correlation. So let's take a walk through the reading. There's a good white text example we'll walk through, and then we will walk through example 17. All right, let's start with the white text example. Suppose an analyst is examining the relationship between returns for two investment funds, A and B, of similar risk over 35 years. She is concerned that the assumptions for the parametric correlation may not be met, so she decides to test Spearman rank correlations. Her hypotheses are that the correlation equals 0 versus not equal 0, the correlation between A and B, the returns between A and B. She gathers the returns, ranks the returns for each fund, and calculates the differences in ranks and the squared differences. So take fund A and arrange it from highest to lowest and then rank them. Take fund B, do the same thing, then put them back the way you found them so that year 1 is fund A and fund B with their respective ranks. Take the difference between the ranks, 27 minus 34, there's your difference, and then square it. Let's scroll all the way down, and you'll sum all of the squares. And then to calculate the correlation coefficient, it's 1 minus the summation ratio here, 6 times the sum of the squared deviations, or the sum of the squared differences. I shouldn't say deviations, squared differences, divided by n times n squared minus 1. Since our n is 35, we'll have this. There is our correlation coefficient, 0.6916. And then we would just use the t-statistic the same way we've used it with the parametric test, except we arrived at our correlation coefficient through a non-parametric method, but we'd still use it the same way. 1 minus, and there is RS squared. We get 5.5005. And we have a two-tailed test, 5% level of significance, critical values, n minus 2. We have 33 degrees of freedom. Critical values are plus and minus 2.0345 because, again, that t-distribution is symmetrical. If you're using an Excel function call, you only have to find one of the tails. Either enter the probability of 0.025 or 0.975 along with your 33 degrees of freedom. You'll get this statistic, 5.5. So we would reject the null. There seems to be a significant correlation between the returns. Example 17, testing the exchange rate correlation. And this one has a correlation matrix or a parallelogram, and there are 10 correlations in there. The example only gives the test for one of the correlations. You would run the test on all 10 of the correlations, but it gives you the blueprint for doing it on one, and then you would, if you want more practice in calculating the test statistic, you can do it for the other 9. An analyst gathers exchange rate data for 5 currencies relative to the US dollar. Upon inspection of the distribution of these exchange rates, she observes a departure from normality, especially with negative skewness for 4 of the series and positive skewness for the 5th. Therefore, she decides to examine the relationships among these currencies using Spearman rank correlations. She calculates these correlations between the currencies over 180 days, which are shown in the parallelogram in Exhibit 26. In this parallelogram, the lower triangle reports the pairwise correlations, and the upper triangle provides a visualization of the magnitude of the correlations, with larger circles indicating larger absolute value of the correlations, darker circles indicating correlations that are negative. So here we are, and here are our correlations that we need down here, and there are 10 of them. For any of these pairwise Spearman rank correlations, can we reject the null hypotheses of no correlation? So our null is there is no correlation. Our alternative is there is correlation at the 5% level of significance. Our alternative is that there is correlation. So critical values for 2.5% in each tail of the distribution are plus or minus 1.97338. And we just have to calculate the test statistics. You can take any of these at random and plug them into the test statistic. It uses this one right here, 0.6079, between the Euro US and the Aussie US, 0.6079. So the calculated test statistic is R multiplied by the square root of the degrees of freedom over the square root of 1 minus R squared. We get 10.2144. And you would have to do that for each of the 10 correlations. They've already done that for you and gave you a table of all the T statistics. So you can scan it very quickly for anything less than 1.9738 or greater than negative 1.9738. And we can see that they all are greater than 1.9738 or less than negative 1.9738. So we would reject the null in all instances. The analyst should reject all 10 null hypotheses because the calculated T statistics for all exchange rate pairs fall outside the bounds of the true critical values. Explain tests of independence based on contingency table data, and we sort of had a quick look at this in an earlier reading, so now we'll do it in a little bit more detail. Tests of independence, we're going to test if classification types are independent. So what do we mean by them being independent? So here's a good question that gets to that matter. Are growth stocks equally likely to be any size, or are they more likely to be large cap stocks? So if we take growth and value, and we take mid cap, small cap, and large cap, if they're independent, we would not expect to see any one cell dominating. However, if they are dependent, let's say we look at healthcare, for example, and we find that healthcare is predominantly large cap stocks, very few small cap. We would say that that is dependent. They are not independent, that the size of a company has something to do with the classification, and that whatever classification we choose, we can almost tell what size companies we would have in that particular industry, or can we not tell? So if I say technology, are technology stocks more likely to be small cap, mid cap, or large cap? And if they are independent, the answer would be it wouldn't matter. They're equally likely to be any size. However, if we find that they are predominantly large cap, that's dependency. So how do we test after we have this classification and we have a contingency table with all these entries? How do we test whether or not they are independent? All right, there are a number of steps involved in getting this done. We start with a contingency table. Here we have value, growth, and blend crossed with small, medium, and large size firms. And our null hypothesis is that these classifications are independent. And the alternative, if we reject the null, the alternative is that they are not independent. So we are going to perform a non-parametric test of independence. It's distributed as a chi-square variable. The degrees of freedom are the number of rows minus 1 times the number of columns minus 1. This is a right tail test only. To understand why, let's draw out our chi-square distribution, which kind of looks like that. And there is our right tail. Well, anything below the right tail, independent, independent, all the way until it's no longer independent. So you can't claim that it's not independent on both sides. It either is or it is not. So as we move towards the right tail, we're independent until we trip that critical value, then we are no longer independent. So it's a right tail test only. This is the test statistic, and I should put square brackets around here to indicate that it is not the sum of the squared deviations divided by EI. It is the sum of the squared deviations divided by EI. That means we do this for each cell that we're in. We don't just do it for all the cells and then divide once by EI. We're dividing each and every time by the expected value. M is the number of cells. Since here we have a 3 by 3, we have 9 calculations we're going to do, which means this summation goes from 1 to 9. OIJ is the observed value in each cell, I being the row, J being the column. EIJ is the expected value in each cell. When we have a contingency table, we're given the observed values. We don't actually have to calculate those. We compile them. There they are. We can see them. But what is the expected value in that cell? So the first thing we have to do is create a matrix, or a contingency table of the expected values. And we calculate the expected values this way. We take the row total multiplied by the column total divided by the overall total. So let's fill in a couple of cells here. We'll fill in the 46.703. I put the expected value for SV, for small and value. So if we sum across, we have 503. And the column total is 148. 503 times 148 divided by the total amount, which is 1594. We get 46.703. So we should expect to see 46.703 firms in that cell. We have 50 firms in that cell. Fairly close. Let's take EMG, that's medium in growth, which is this one over here. And that's 366 by 381. 366 by 381 divided by the 1594, we get 87.482. We observe 122. Well, that is different. It's much higher. Our observation is much higher. So we need those two tables first. Then we can calculate the difference between the observed minus the expected squared divided by the expected. So let's see if we can recover one of the numbers in here. Let's recover our value in the very first cell. What is our observed? Our observed is 50. What is the expected? The expected is 46.703. Subtract them and square them and divide them by the expected value. We get 0.2328. And this is just 3 decimal place, 0.233. We do that 9 times. After we do that 9 times, we sum them up. Right here, we sum up all 9, and that will give us our t-stat. Our t-stat. Our chi-square stat. So to put it all together, our null hypotheses, we're saying that size and type are independent. Our alternative is just the opposite. Size and type are not independent. We've already shown how we calculate the value in each cell for the test statistic. If we sum them up, if we sum all of the values up, we get 32.0825. We need a critical chi-square value now. Since we're putting in a probability, remember this is right-tailed only. So if it's right-tailed only, 95% of the probability is in the do not reject region. So 0.95, our degrees of freedom. 3 minus 1 times 3 minus 1, 2 times 2 is 4. It's number of rows minus 1, number of columns minus 1, and we'll get 9.4877. We're at 32.08. We're way over here, and this is this value right here. So we're going to reject the null. They are not independent. However, we get to this conclusion, they are not independent. Because of the nature of what we're doing, all the entries in this table here, all of the values that we sum to get the chi-square test statistic will be positive. So it tells us nothing about, well, being that we conclude that they're not independent, are we seeing more than we should or less than we should if they were independent? It doesn't tell us that because they're all positive. So we can calculate standardized residuals, which is just the observed value minus the expected value divided by the square root of the expected value. And if this term is greater than 0, it means that we're witnessing more observations than would be expected if they were independent. And if it's less than 0, it means we're witnessing fewer observations than we would if they were independent. So let's take 2 of the cells. We'll take S and V, that's small and value. We'll take MG, which is medium and growth. So we're looking at these 2 numbers here. They would have to be positive just by the nature of the way we calculate them, but what is that telling us about the observations? Are we seeing more than we should if they were independent or fewer? So we calculate 0.048 and 3.69, they're greater than 0. That means we are seeing in those cells more than would be expected if they were independent. And you can do that for all nine cells. Once you do a couple of them, you can see the pattern. The rest is repetitive. I do encourage you to do the repetitive work because it's with repetition that we then begin to say, okay, I now see how it's done. It becomes part of you as opposed to doing it once, or worse, just reading it once without actually doing the work yourself. Actually doing the calculation really reinforces it. So I do encourage you to try to recover more numbers from the exhibits that are there. Let's do a walkthrough of example 18, and then we're done with this reading. Example 18, using contingency tables to test for independence. Consider the contingency table in Exhibit 32, which classifies 500 randomly selected companies on the basis of 2 environmental, social, and governance rating dimensions, environmental rating and governance rating. So when we look at the table, it looks fairly even across all the cells, except our eyes are drawn to the 130 over here and the 5 over here. It seems like something is there. Looks like there's some kind of dependency there, while the others seem fairly evenly distributed. However, eyeballing this is not going to give us an answer. What are the expected frequencies for these two ESG rating dimensions if these categories are independent. And how we get that, if we look at the first cell, progressive and progressive, we take 80 multiplied by 155 divided by the 500, and that will give us an expected value. For average and progressive, we see 80, but we would take 260 multiplied by 155 divided by the 500, and that will give us an expected value. So we can see that they've done this one for the first cell, 24.8. If we scroll down to Exhibit 33, there are all the expected values for each cell. Number two, using a 5% level of significance, we know this is one-tailed, it's right-tailed only, determine whether these two ESG rating dimensions are independent of one another. And to do that, we're going to have to take the observed value minus the expected value we calculated, divided by the expected value, and we're going to have to do that for every cell. So we can see in the first cell here, 4.195. That is the observed value minus this expected value of 24.8. Divided by 24.8, we get 4.195. Do that for each of the 9 cells. Here are each of the 9 values. If we add up these 9 values, that's our chi-square test statistic. So let's go through the formal process here. State the hypotheses. The null is that they are independent. Governance and environmental ratings are not related, so these ratings are independent. I don't think you have to say they're not related. I think it's just enough to state that you could just state the two ratings are not, are independent versus the alternative, they are not independent. Identify the appropriate test statistic. It's a chi-square test statistic of this form. State the level of significance, 5%. State the decision rule. We have a 3 by 3, so it's 3 minus 1 times 3 minus 1. We have 4 degrees of freedom. It's a one-sided test, 5% level of significance. Here is our Excel function call, 0.95 and 4. And you will get a critical value of 9.487729. All we have to do is add up all of these numbers in this table. We get 35.74415. Way larger. It's way further in the right tail than 9.48. We're going to reject the null. These categories are not independent. Reject the null hypotheses because the calculated chi-square test is greater than 9.48. There is sufficient evidence to indicate that the environmental and governance ratings are related, so they are not independent.